Okay, let's continue part 2 of lab 10. And as you can see, we first read at address 00. It causes a miss. 03, another miss, because we have both valid bit as 0. So that means earlier when we first turn on the computer, the caches contain junk. Therefore, all the valid bit must be initialized to 0. Okay? And after we first read the data from DRAM, the cache will contain useful data. Therefore, the valid bit will become 1 later on. Okay? And we are going to continue reading at address 04, 06, 09, 0A, 0C, and 0F. All of them cause the misses. Okay? Because 03 is here, 04 is next, so 04 correspond to another cache block. So earlier it was 0, the valid bit was 0, so one more miss, and then we skip to 06, 05, 06 here, so it's located in another block which was invalid again, and all the way now to 0F, which is this location. Okay, so valid bit becomes 1 as these 2 bytes are copied and put here, but 0F correspond to this location. Alright, therefore totally 8 cache misses. Okay, and again 0F location correspond to 1 1 1 1 base 2. Okay, so these 4 bit correspond to F. Okay, now you understand a little bit about cache more, but in this experiment our cache size and our memory size are the same, therefore we don't need a tag here. Okay, in the next experiment we will increase the RAM to be bigger than the size of the cache, but we keep the block size the same. Okay, so refresh the button on the web browser to restart the new experiment, and then put the address bit to be 6 bit, which will create 64 bytes of memory and cache size of 16, block size of 2 bytes. So you will get something like this in your experiment window. Okay, so I will explain the physical or the DRAM again. Earlier we start from 00, which is this location, and then we continue 01 all the way to 07, and now this will be 08 all the way to 0F, and now the next row 10, which is this location 11 all the way to 17 base 16, and then 18 all the way to 1F base 16. Okay, and right here is going to be 38, 39 all the way to 3F base 16. Alright, so totally 64 bytes. But the cache size stay the same, 16 bytes, and the block size is 2 bytes as our first experiment. Okay, so now let's start with the location F. Oh no, let's start with location 01, 02, 03. Okay, so 01 cause you a miss. Why? Because 01 correspond to this location. Can you see that? F6, it correspond to this. So earlier the valid bit was 0. Now it becomes 1. Okay, so 02 is this location 02 EF. So it right there in the cache, and again valid bit was 0 and now become 1. And as you can see, the next address is 03, which is this location 03. It contains EA, which correspond to this EA. Okay, therefore EA is already there, so it's a hit, HIT hit. Okay, so you can see the number of hits changes from 0 to 1. Okay, and once you start reading all the way to 0F, right here, 0F, you're gonna get 7 hits and 8 misses. Okay, and for location 0F, as you can see, 0F base 16, this part correspond to F 1111 base 2. Okay, and 0 can be expanded to be 000 base 2, which correspond to this part, the tag. Okay, these 2 bits correspond to the tag. Okay, now we are going to continue the reading of memory, and we continue at 10. What is 10? Okay, so as you can see here, 10 will correspond to 1 here and 0 here. So 0 base 16 will be expanded to be 0 base 2, and 1 can be expanded to be 1 base 2. Okay, and this number, as I showed you earlier, correspond to block number 0. Okay, and you can see from the previous figure that block number 0 contains 0 as a tag. This T correspond to the tag. Okay, and this tag is in base 16. Okay, so our tag now for address 10 base 16 is 1, not 0. Okay, therefore we can tell that, oh, they are from different memory locations. Okay, this cache block contains something, not something that we are looking for. Okay, therefore it causes a miss. Okay, as you can see, it was 20 earlier, right? It contains this block, but right now we want to read these 2 bytes, and these 2 bytes are not in this memory location yet. They are not in the cache yet. Therefore, we need to copy this into the cache, okay, and change the tag from 0 to 1 to be this tag. Alright, so this example or this experiment will show you the concept of the tag. Okay, and from 10 we are going to read location 11, 12 all the way to 1F. Okay, therefore you will see that it's going to be a lot of hit and misses. Okay, I think this figure is wrong. Okay, this figure is wrong. I need to replace. Okay, so in the next experiment, let me explain it more a little bit. The right figure should be, the tag should be all the way 1 and 1 and 1 and 1 and 1 and 1 and 1, and these 2 memory rows will be copied to the cache. Okay, so the next location will be 1A, CA, 35, 95, okay, all the way to F6, E5, okay, dot 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 dot. Alright, next experiment is the RAM of 64 bytes, cache of 16 bytes, and block of 4 bytes. Okay, so the memory stay the same, but the configuration of our cache is different now. As you can see, each block contains 4 bytes. Okay, and now for the total of 16 bytes, we have 4 blocks multiplied by 4 bytes. Okay, so we only have 4 blocks right here of block 0, block 1, block 2, block 3. Okay, and as normal, the valid bits are 0 at the beginning. Okay, and then we are going to read the address of 00 to 0F all the way. So please capture your experiment window. Okay, and then we are going to read 10 all the way to 1F and capture the experiment window. Okay, and that's it for the experiment. Now I hope you understand how the direct map cache works, and do the exercise 1 and exercise 2. Okay, they are pretty much the same, but with different configuration. RAM of 64, cache is now bigger to be 32 bytes for block of 4 bytes, and in exercise 2 we keep the RAM size and cache size the same. Now we increase the block size to be 8 bytes. Okay, and we are going to do the same activities. Read the address from 00 to 0F okay, and capture the screen. And then in exercise 2B, compare the number of cache hits and miss with section J3 and J4. Explain the result in handwriting. Okay, J3 and J4 are right here, J4. Okay, so you can capture the number of cache hits and misses. Okay, when you read from 00 to 04 to 0F, so don't forget to capture the number of cache hits and miss to be compared with exercise 1 and 2. Okay, in exercise number 1, we read 00 to 0F, just like exercise number 2, and compare the number of cache hits and miss. Okay, now when you compare the cache hits and miss, you have to be able to explain, okay, what's going on. Especially in this case, exercise 1, remember, we keep the block size the same. We increase the cache size from 16 to 32. So what happened? Alright, and in exercise 2, we keep the RAM and cache size the same, but this time we increase the block size from 4 to 8. So what happened? Okay, so you should be able to explain when you change the system parameters. Okay, thank you very much. Bye bye.